One-dimensional steady-state heat conduction without heat generation through homogeneous and isotropic material having constant thermal conductivity K with respect to temperature. So let us discuss the heat conduction through hollow sphere under above mentioned conditions. One such hollow sphere is shown in figure having the material thermal conductivity K, its internal radius R1, outer radius R2, and let's say any radius R at which we want to find out the temperature variation. The internal surface at radius R1 is having temperature T1 and outer surface at radius R2 is having temperature T2, and the temperature at any radius is T suffix R. In this sphere, heat can flow in three different directions, but I am considering heat transferred only in radial direction. I am not considering any heat flow in the tangential direction and in azimuthal direction. So no rate of heat transfer, no rate of heat transfer in both these two directions. So no heat transfer either in tangential direction and in azimuthal direction. Also, I am considering the material of this sphere is homogeneous, so having constant K with respect to radial, tangential and azimuthal direction. Since inner surface temperature is greater than outer temperature, heat transfer will take place from inner side of the sphere to outer side in the radial direction only. So from electrical analogy of the heat transfer, let us draw equivalent electrical circuit for the heat transfer through plane wall. Flow quantity will be heat transfer and potential difference will be temperature difference between inner and outer surface of the sphere, and the material of this sphere is going to offer one thermal resistance in the path of the heat flow. So this RT sphere we are supposed to calculate. Right now I don't know its value. Now let us write down the aim of this analysis. As we have already mentioned, in case of plane wall and in case of cylinder, temperature variation of the sphere, that is T, will be function of radial direction only, since we are assuming heat conduction only in radial direction, and by virtue of this heat transfer is taking place. So we are interested to calculate rate of heat transfer. Now since it is a spherical body, so in order to achieve aim 1 and 2, we have to recall generalized heat conduction equation in spherical coordinates. We have already derived this equation. So do you remember this? It is bit tricky to remember. So 1 over r square del over del r square del square t over del r plus 1 upon r square sin square theta del square t over del phi square plus 1 over r sin theta into del over del theta sin theta del t del tau plus q dot g over k is equal to 1 by alpha into del T over del tau. This is the generalized heat conduction equation where this term is due to heat flow in radial direction. This term is due to heat flow in the tangential direction, and this term is due to heat flow in the azimuthal direction. This is heat generation rate, and this is thermal diffusivity, and this takes into account sorry, variation of temperature with respect to time. Now since we are considering one-dimensional steady-state heat conduction without uniform heat generation through homogeneous and isotropic materials, so we have to apply all these stipulations to this equation. Let's say this is equation number 1. So what are the stipulations associated with this analysis? The stipulation number 1, we are talking about one-dimensional heat conduction only. And that is also in radial direction. So, as a consequence of this stipulation, any heat transfer and temperature variation in the tangential direction will be 0 and in the azimuthal direction as well. Sorry, this term, please correct this. This is theta. Del T over del theta will be equal to 0. That is, there will be no heat transfer in either tangential and radial in azimuthal direction, and there will be no temperature variation of the sphere in this direction. Stipulation number 2, we are considering steady state. So what does it mean? Variation of temperature with respect to time will be 0. We are considering no heat generation within the sphere So this q dot g will be 0. Now applying all these stipulations, applying above stipulations to equation 1 will give, what it will give me? One over r square del over del r into r square del square t over del t. Sorry, here it is not del square, it is del t over del r. And right hand side will also be equal to 0. So this equation will reduce to one-dimensional form. And in the limiting case, this equation will reduce to 1 upon r square d over dr r square dt over dr is equal to 0. Since 1 upon r square cannot equal to 0, hence we can also write this equation as d over dr r square dt over dr is equal to 0. Now this equation, what we got is called as, let's say this is equation number 2. So what is the significance of equation number 2? Equation 2 is governing equation for heat conduction through plane sphere. What is the meaning of governing differential equation? If I solve this equation, the solution of this equation will give me variation of temperature of the sphere in the radial direction. So in order to get that variation of temperature with respect to any radial distance r, I have to solve this expression. Now, how to solve this governing differential equation? This is a second order differential equation. In order to solve it, to get the expression of temperature variation, I have to integrate it twice. So first integration will give me r square dt over dr. Let me write it in general way. is equal to integration of 0. So if I integrate it, I will get r square dt over dr is equal to C1, or dt over dr is equal to C1 over r square. So I got these two expressions. Both are important. So let's say this is equation number 3 and this is equation number 4. Once again I have to integrate this. Before that I have to rearrange this dt, rearrange it, and I have to integrate it. So it will give me integration of dt. C1 is a constant, dr over r square. So second integration will give me t is equal to minus C1 over r plus C2. Let's say this is equation number 5. Now equation 5 once again is a very important expression. Equation 5 gives temperature variation of sphere with respect to any distance r. As you can see here, if I put the value of r, I will get the variation. I will get the value of temperature at that point. However, what is the problem with this expression? I don't know the value of C1 and C2. These are the constants and both are unknown. That is, I must have their values in terms of some known values like temperature T1, T2 and radius R1 and R2. In order to solve the expressions for C1, C2 in terms of known values, I have to apply some boundary conditions. Boundary conditions means known value. So what are the boundary conditions we can have? We know at the inner surface of the sphere, that is at R is equal to R1, temperature is T1, and boundary condition number 2, at the outer surface, that is R is equal to R2 of the sphere, temperature is T2. Now let us apply these boundary conditions to equation 5. It will give me two expressions. That is, for first boundary condition at R is equal to R1, E is equal to T1 is minus C1 over R1 plus C2, equation number 6. And at second boundary condition at T is equal to T2 minus C1 over R2 plus C2. So we have got two simultaneous equations. Now if I solve these two expressions, I can have the value of C1 and C2. So solving these two, I will get the value of C1 as T1 minus T2 over 1 over R2 minus 1 over R1, and value of constant C2 as T1 plus T1 minus T2 over R1 into 1 over R2 minus 1 over R1. So this is the value of C2. So putting the values of these constants C1 and C2 into equation, what is that equation? Equation 5. It will give me the expression for T is equal to minus T1 minus T2 over 1 over R2 minus 1 over R1. This is the value of C1 and it is divided by R, plus value of C2 as T1 plus T1 minus T2 over R1 into 1 over R2 minus 1 over R1. So this gives me the variation of temperature with respect to time. Further, I can simplify this. T is equal to T1 minus T2 over 1 upon R2 minus 1 upon R1 is a common term. Then T1 is also there. So 1 over R1 minus 1 over R. Let's say this is equation number 8, I think. Yes. So equation number 8 gives you the variation of temperature with respect to time at any radial distance r. So as you can see here, T1 is known to us, T2 is known to us, R1, R2 values are known to us. So if I keep on changing the value of R, I'll be getting the value of temperature at that point. So equation 8 is temperature distribution. Equation 8 will give me temperature variation or temperature distribution in a hollow sphere. So only unknown is R. So putting the value of R, it will give me the temperature at that radial distance inside the hollow sphere. Further, let us write down this equation in the non-dimensional form. So it will give me another important conclusion. So above equation in non-dimensional form, how can I write this? T minus T1 over T2 minus T1 is equal to 1 over R minus 1 over R1 divided by 1 over R2 minus 1 over R1. This is equation number 9. So what are the important conclusions I can draw from equation number 9? It is that this equation is nothing but equation of hyperbola. So what is the important conclusion I can get from equation number 9? Temperature variation in the sphere is in the form of hyperbola. The shape of the curve will be hyperbolic in nature. So like we have seen in case of plane wall, the temperature variation is linear, represented by a straight line across the plane slab, two faces at two different temperatures. Similarly, in case of cylindrical wall, we have seen the temperature profile shape is logarithmic, and in case of plane sphere or hollow sphere, the shape of the temperature profile will be hyperbolic in nature. Please remember these three things. Now, after finding out the temperature variation, let us find out the rate of heat transfer, the equation for rate of heat transfer. What will be the equation for rate of heat transfer through this sphere by virtue of heat conduction in the radial direction? Once again, we are considering one-dimensional steady-state condition, so we can recall Fourier's law of heat conduction. And this equation is nothing but Q is equal to minus K into A into dt over dr, where the dr is the thickness of the element in the direction of heat flow. Now from equation 3, what is equation 3? This is the equation 4. dt by dr is equal to C1 over R square. So from equation 4, we can put the value of dt as Q is equal to minus Ka C1 over R square. Let us put the value of C1, which is nothing but T1 minus T2 over 1 over R2 minus 1 over R1 and divided by R square. this way I can get this. Now if I take into consideration the minus sign, the expression will become Q is equal to A, where A is area of the sphere normal to heat flow, and for sphere this area is nothing but 4 pi r square. So I can put the value of area as 4 pi r square T1 minus T2. I am taking into consideration this minus sign, so this entire term will become 1 over r1 minus 1 over r2 r square. This r square will get cancelled, so I can simplify this. A into 4 pi into T1 minus T2 over 1 over R1 minus 1 over R2. So this is the rate of heat transfer through the plane sphere. So another important equation we have got. So let me underline this. This is the rate of heat transfer, and what will be the number of this equation? Equation number 10. So both the M's we have achieved. We could find the temperature variation within the wall, within the spherical wall. We can calculate the heat transfer rate through the spherical wall having radius R1, R2 and temperatures T1 and T2 respectively. Now another thing, another important relation we can have to this analysis is thermal resistance. So rearrangement of above equation will give, let us rearrange into the form of potential difference, that is temperature difference, and thermal contact resistance. So it will become 1 over 4 pi A 1 over R1 minus 1 over R2. So if you compare this equation with the standard form we have, in this form, this equation comes from electrical analogy of heat transfer, where delta T is potential difference and RT is called as thermal resistance. So if I compare both these two equations, from this equation we will get the expression of RT as 1 over 4 pi K 1 over R1 minus 1 over R. And this is nothing but thermal resistance offered by spherical wall. This can also be written in another form as R1 R2 over extremely sorry, R2 minus R1 over 4 pi K R1 R2. So this is the expression of thermal resistance offered by spherical wall. So another important equation we could derive for thermal resistance offered by spherical wall. And let us say this is equation number 11. So from this expression we could get, from this analysis we could get temperature variation within the sphere by virtue of heat transfer. We could also get the equation for rate of heat transfer by virtue of temperature difference for spherical wall, and finally we could get expression of thermal resistance offered by spherical wall to the path of the heat flow. So now we have thermal resistances for plane wall L upon Ka, for cylindrical wall 1 upon 2 pi Kl log of R2 by R1, and for spherical wall R2 minus R1 over 4 pi K R1 R2. Now let us do some more analysis. Let us get logarithmic area for the hollow sphere. We could get this logarithmic sphere for cylindrical wall as well. Now what is the need of this logarithmic area? Quite often it is convenient to write the heat flow equation through a sphere in the same form as that for heat flow through a plane wall. In this case, the thickness L of the slab or plane wall will be equal to R2 minus R1 for sphere, and the area will be an equivalent area AM. Let's say this is the sphere, hollow sphere of radius, inner radius R1, outer radius R2, and this is the plane slab. So we want to write the expression for the hollow sphere in the same form as that written for this plane slab. This slab is having thickness L, thermal conductivity K, temperatures difference across its faces as T1, T2, and temperature difference across the sphere is T1, T2, which happens to be same. Thermal conductivity of this sphere material is K. So whatever area of the slab we will get, that area is called as equivalent area. Now to get the equivalent area of this slab, we must have rate of heat transfer through a sphere is equal to rate of heat transfer through this plane wall. Just now we could derive this. Q is equal to 4 pi K R1 into R2 over 1 over R1 minus 1 over R2. And for heat transfer equation from plane wall will be Ka T1 minus T2. There will be temperature difference as well. Ka T1 minus T2 and L will be R2 minus R1. Here, the area of the slab will be equivalent area. So after simplifying this, what I will get, this K will get cancelled because I am taking the same thermal conductivity. I am also considering same temperature difference. So what I will get, 4 R1 R2 over R2 minus R1 . Oh, sorry, this will not be there. 4 pi K even minus T2. After simplifying this, I will get 4 pi R1 R2 into R2 minus R1 into AM over R2 minus R1. This will also get cancelled. From this, I will get the expression for geometrical logarithmic area or mean equivalent area of the sphere as 4 pi R1 into R2. This is called as equivalent area or logarithmic area of the sphere. If Rm is mean radius, so Am can be written as 4 pi Rm square is equal to 4 pi R1 R2. From here, the mean radius of sphere will be square root of R1 and so this way I could get expression for mean radius of sphere. It is nothing but square root of R1 into R2.